Thank you. Welcome back. So the second talk here is discussion on the design and execution of validation studies for mixture interpretation procedures. A couple of points to make beforehand. Validation talks are always enlightening and exciting, and I know it's before lunch, so we'll carry on here. So going back to this slide here on the elements of your mixture interpretation, we're looking at the principles behind, or the theory behind mixture interpretation. So looking at the SWGDAM guidelines, the ISFG recommendations, other papers in the literature, using that to develop your protocols and doing validation studies. Those will translate into your laboratory SOPs. And so we had a question during the break. I'm sorry I didn't bring it up, but I'll try to summarize. The question is, if the SWGDAM guidelines are not audited, if you're not audited by them, how then in court, if you're asked the question, are you following the SWGDAM guidelines, how can you, sort of give some type of evidence or proof of that? Then you can simply say, well, part of the guidelines suggest, or the purpose was to encourage labs to look at and review their SOPs and their validation studies. We've done that, and we feel that we don't need to change our thresholds. We already have an analytical threshold. We already have a stochastic threshold. So these are already established in our SOPs and so forth, and those SOPs can be evaluated by, whomever. So that's one way that you could address that, since there's no sort of document that says you are following the SWGDAM guidelines, check. But using that protocol, that SOP, then into practice with training and experience within your laboratory. So some common perceptions of validation, of course, is that it takes a lot of effort, so you need a lot of experiments to do validation, and it takes a significant amount of time to perform the studies. So the goal is not to mimic every possible scenario that you would expect to see during casework, because every case is different. And so the goal of the validation studies is to help you understand your system. So information from your validation studies should be used to set laboratory-specific peak heights, minimum peak heights or detection thresholds, stutter percentages, peak height ratios, and relative balance across loci. And these values are all dependent upon the amount of input DNA. So if you're amplifying low input DNA, so I put in one nanogram of the extract. Well, if it's 900 picograms belong to the female and 100 picograms belong to the male, then you're in this low-level DNA range, or at least approaching it. And so you're talking about stutter percentages maybe higher, peak height ratios maybe lower. So with low-level DNA, you're not following the same types of, you're not observing the same types of phenomena that you see with high levels of DNA when it comes to peak height ratios and stutter percentages and so forth. So as we mentioned earlier, two types of thresholds here. Analytical threshold, which is based upon your instrument sensitivity and can be impacted by the instrument baseline noise. This can change if you have a new laser installed into your instrument. So these are things that can impact your thresholds. And your stochastic threshold, which is dependent upon the biological sensitivity of the system, which can be the kit that you use or the types of injection parameters and so forth. So these are places where validation studies should be performed. So again, we're looking at the signal to noise here. At the last year in October, at the Promega meeting, the International Symposium of Human Identification, Robin Cotton and colleagues at Boston University and John Butler and I and Charlotte Word, we put on a mixture workshop, and the intent was to use these which we'll try to use on Thursday, these little clickers that you can anonymously answer questions. And so unfortunately we didn't have the clickers, but we still asked the questions during our presentations, and we asked people to write down their response on a piece of paper. And then Robin had some students to compile all of this data. And one of the questions we asked at that Promega meeting, 113 people responded, is what is your analytical threshold? 5 labs said less than 49 RFUs. The most frequent response was 50 RFUs, but there were 6 labs that said, 7 labs that said greater than 150 RFUs. So you can get a range of analytical thresholds, and again, it's all dependent upon your instrument, your instrumentation. There were several people that said I don't work in a lab, because in the audience were also attorneys and so forth too. So when developing your analytical threshold, if you look at the guidelines, it gives a recommendation, but it's not meant to be this is how you do it. There are multiple ways to develop an analytical threshold. So in section 1.1, as an example, the threshold may be twice the intensity difference between the highest peak and the lowest trough, but other methods may be used. So there's no one way to develop your analytical threshold, and we'll take a look at some of the different methods. How do you develop that analytical threshold? Do you simply use negatives? Do you use blanks? Do you use your positive controls? Because this can make a difference. So this is an example here looking at a negative, where the maximum height here of the highest peak observed in the baseline is at 15 RFUs. And then if you take a look at a positive control, you can see that the highest peak observed in the baseline is 37 RFUs. So it can be different. Where do you look for these highest peaks? Well, you can look across the range. There's a paper that I'll talk about in the enhanced methods discussion by a group in the Netherlands by Antoinette Weston et al. They looked at this region between 250 and 295 base pairs because in this region there's typically no dye blobs. You typically you won't see bleed through from your size standard. So this is a good region here where you won't have extraneous artifacts in the way. Of course, you can always have spikes and other things to occur in this region, but they used this particular region to develop their analytical threshold since it was free of dye blobs and bleed through from the size standard. You could also, once again, develop analytical thresholds for the different dye channels, because of the differences in the noise. New instruments, new thresholds. So, of course, the 3500, the ABI 3500 is now out, and of course, we all know that ABI is retiring the 3130 eventually. So at NIST, we have recently purchased a 3500, and we are looking at the thresholds here with a 3500 with a default injection, 50 RFUs is the highest peak we observed. So we would say our analytical threshold, depending upon how you determine your threshold. Could be 100 if you take twice that, or 150 if you multiply it times 3. So you're looking at an analytical threshold at 150 RFUs, whereas on the 3130, we saw 16 RFUs. Other ways, so again, the SWGDAM guidelines say one way you can do this is to take twice. I call this the ballpark because that's sort of what we're using at NIST, is we take 3 times the highest peak. It's a different way to do it. Jason Gilder and Dan Crane's lab determined the limit of detection by looking at positives, negatives, and reagent blanks from 150 cases. So they took the average peak and the baseline plus 3 standard deviations. So they published this in 2007. So here they determined the limit of detection for this particular sample was at 29 RFUs in this particular mixture. Once again, you can have variability depending upon the type of sample that you use. So you can see positive control, the maximum peak observed, the maximum peak observed in your baseline was 27. The average was 27 RFUs, but if you use a negative, they saw 53 RFUs. So the type of sample that you use can cause some variation here. Catherine Grishek, who is at Boston University with Dr. Cotton, she presented at the Promega workshop. Her lecture was on analytical thresholds, and so she did a very nice job of presenting alternative ways to calculate analytical thresholds. And so her presentation is on Starbase. If you go to Starbase, we have a section that's dedicated now for mixtures, and in that link, on that page, you can find all of the presentations that we gave at the Promega meeting. And so you can pull up Catherine's talk, and you can see what she presented. So I'll show you a few slides from her presentation. So there are different ways that you can calculate or determine analytical thresholds. The 3 methods presented here uses negative controls. So the Dan Crane paper, the Jason Gilder paper from 2007, used this method that's an IUPAC 1976 Kaiser method. So it's using basically the same method of taking the average plus 3 standard deviations. Here's another method from 1995, and then using the example in the SWGDAM guidelines. And then you can also use from DNA dilution series, so using controls, you can determine the threshold too. So there are different formulas that you can use to calculate. So this is the math. So John Buckleton is happy now. We've got some formulas here. So, but this is sort of the methods that you can use for calculating your analytical thresholds based upon the different methods. The 3 that use negative controls, and she recommends at least 20 different negative controls here. And then using these 2 methods here, incorporate DNA from dilution series. And based upon that, for the data that she was observing, the data she was using, you can get different analytical thresholds depending upon the method. So you can have an analytical threshold as low as 4 RFUs using method 2, or as high as 39 RFUs using method 5 with the DNA dilution series. So everyone says, okay, well, this is a validation talk. Just give me the right answer. What do I need to do? Well, John Butler would say, shame on you. But so there's no right answer. This is what you have to do in developing your own protocols and what you feel comfortable with your data, your instrument. Every instrument is different. I'm sure if she ran these negatives on your CE, she would probably get different values. So you have to develop these for your lab using your instruments and your kits and so forth. As I mentioned earlier, the analytical threshold is the floor of your electropharogram. So even though you may see little peaks below the analytical threshold, they're not to be trusted. And so you can just look and look and look and look and try to see peaks, and you'll end up, kind of like isealylic peaks. They're everywhere. They don't even know that they're peaks, but be careful of that. So to set your stochastic threshold, Peter Gill just published a paper in 2008 about how to determine the dropout threshold or the stochastic threshold. So Peter recommends that you can determine this experimentally for an analytical technique from a series of DNA dilutions of known genotypes. And so you determine the point where the dropout of a heterozygote is observed relative to the size of the survivor companion allele. And the threshold is that point where you see the maximum size of your companion allele. And this is also the point where the probability of dropout approaches 0. So I mentioned that earlier. Actually, I think I have that. So let me just mention here at the end, dropout thresholds will change depending upon the instrument and assay conditions. So if you increase your CE injection time, you're going to be increasing your stochastic threshold and your analytical threshold too. So we'll talk about that in the next talk after lunch. So this is the paper here from Peter Gill, and this is the example I mentioned. So at this point here, this peak is just below, say this is 150 RFUs and this is at 149. Okay, so technically it's below threshold. However, the probability of dropout at this point is pretty low, approaching 0. Once this peak starts falling down, your probability of dropout starts to increase. And so John Buckleton has done a lot of work in this arena, as Jack alluded to in his talk, with incorporating these probabilities of dropout and so forth, considering this as part of the analysis. So this is a paper from 2009 about low template or stochastic threshold with the relative risk for national DNA databases. Again, just this table here, this figure here from Peter's paper shows the relative risk. So if your threshold is, say, quite high, like 200 RFUs, the probability you're going to see dropout of say you have a heterozygote and one of the peaks is gone, and the surviving peak is at 250 RFUs, the probability you're going to see that is quite low. And so you can set your threshold at 200, and you can be quite confident that you're not observing any type of extreme dropout. As you move that threshold down to, say, 150 RFU, you go from being in a green zone to an amber zone in which there's some caution that should be considered. So your probability of extreme dropout is possible, but still fairly safe. But this is something that you have to consider. What's your comfort level? Once you start decreasing the threshold down to, say, 75 RFUs, then your probability that you're going to have extreme dropout is quite high. So you're going to be calling homozygotes when, in fact, it's a sister allele with a heterozygote that's lost. So you have to find that comfort range for you, and the way you do that is through your own validation experiments. Here's another paper by Neil's Morling lab, in which they were determining the mean peak heights for different dropout possibilities. So they were trying to come up with, say, at 200 RFU average is where you would have a probability of dropout, about 1% or so. So it's all dependent upon the comfort level at which the RFU value above which it's reasonable to assume that that dropout has not occurred. And so you're looking at this through empirical data. It depends upon the kit that you're using. Of course, kits are becoming more and more enhanced. So the different Identifier Plus and PP16 Hot Start have reformulated buffers and so forth. Potentially, again, these are proprietary components, so we don't know exactly, but we know that you don't add TAC anymore, so there potentially are different polymerases there. It's uncertain, but the thing here is that if you go from doing identifier to doing identifier plus, then you need to reestablish your stochastic thresholds. So I'll give you some examples of what we're doing and what others are doing. Joni Seguela was part of our workshop at the American Academy of Forensic Sciences meeting back in January, and so she gave a discussion about validation. And this is what they did at Massachusetts State Police Lab with Identifier. They used at least two sources, at least two DNA sources, and sometimes they go up to 5. And they do a twofold dilution series. So they go from 5 nanograms, 2.5 nanograms, and so forth, all the way down to 39 picograms. So you're doing your dilution series, and then you establish your analytical threshold first, and then you do your stochastic threshold. And so typically their stochastic threshold is about 3 times their analytical threshold. So if their analytical threshold is 50, their stochastic threshold would be 150. And they also look to see if they obtain a partial profile at 150 picograms. And so they look at the dilution series, and at 150 picograms, which is where you're starting to approach the low template DNA, where you start to have stochastic effects, starting to see where dropout is occurring there. And so you're in this sort of gray zone in the stochastic range. Another possibility, another example, this was Robin Cotton at the Promega workshop, said there's one way you can do it without having to create brand new validation experiments, is to look at some of your real world data. So for example, if you take sexual assault casework data from a known heterozygous, at a known heterozygous loci, so for example, you have data from a 2-person mixture, and say the male perpetrator here is the major contributor, and you have a known victim here who's heterozygote. If you see in your evidence dropout at 150 RFUs, then this could be used to help you establish your stochastic threshold. So you're using real world data, not pristine dilutions, and you're looking at locations where you have a known heterozygote where one allele has dropped out. So that's one way that you could also determine your stochastic threshold. So one thing that we do at NIST is, of course, using multiple samples and replicates and different concentrations to sort of get a feel of how your system is working. So we have 3 samples in our population samples that we run at NIST that are fully heterozygous, the full heterozygote at every single loci. So we do a dilution series of these samples. I know this is extremely hard to see, but I just wanted to make the point. You have to be careful in your sample selection because, just simply using a positive control like 9947A, 5 of those 13 CODIS loci are homozygous. So you're really only getting, 40% of the DNA of your markers are homozygous, and so it's kind of difficult to develop, at what point does your sister allele drop out. But in the SRM 2391B, in the STR SRM, genomic number 8 is fully heterozygous at all of the CODIS loci. So that may be a sample that you wouldn't want to use every single time, but if you're validating a new kit or whatever, that has heterozygote at every CODIS marker. And of course, stochastic thresholds are never cut and dry. They're never perfect. They can vary between loci and different dye channels. So this is something that you have to consider. So this is how we develop or set stochastic thresholds at NIST. So this is identifier, again, just showing you one particular kit. We've also looked at all the other kits, 28 cycles, normal, standard injection, and we develop these heat maps. So if there's a green box, that means that you have a correct genotype, so everything typed correctly. If there's a yellow box, that means you have a dropout of a heterozygote, where one allele has survived, the other allele has completely dropped out. And if you have a red box, this means you have a complete locus dropout, so both alleles are gone. And again, every marker here is heterozygote, so we don't have any homozygote markers present here. So you can see at 0.1 nanograms, at 100 picograms, except for one case at D7, we had this one case here where we had a dropout and there's a surviving sister allele. So for the most part, at 100 picograms, we're fine. When we moved to 30 picograms, we're starting to see dropout, allelic dropout, and locus dropout. So let me just sort of blow this up a little bit. So what we have here is a case where between 30 and 50 picograms, I'm not showing 50 picograms here, but between 30 and 50 picograms of DNA, we're starting to see a lot of yellow boxes and red boxes showing up. Inside of the yellow boxes, we have the RFU of the surviving allele. So we look then in these boxes and we see what is the highest surviving allele present, and that would be at 274 RFUs. So in this case, we may want to just round up to 275 or 200 or 300 if we wanted to develop a stochastic threshold based upon this data. So this is data that Becky Hill generated at NIST. So again, one thing you have to be careful of in developing your stochastic threshold is the point in which your data is considered reliable. And so there's a level of risk involved. The higher you go, the less risk you have of calling a false homozygote. However, you start to lose more data for your statistics. So this is the example with the 274 dropout. So here, if I set my stochastic threshold at 200, well, it's a heterozygote. Both alleles are below 200, but I'm expecting this as a single source, so I'm okay. But here, 200 RFU, stochastic, 274 peak, hey, that's a homozygote. When in fact, it's not. It's a heterozygote with a dropout. So you have to be careful in setting your stochastic thresholds too high, or in this case here, if you're setting it too low, you're going to miss out on this data. Once again, new instruments, new thresholds, new kits. Here's Identifier Plus that we're running on the 3500, and just sort of blow up here this one example. The RFU values for the 3500, it's going to take a complete paradigm shift in the way we think about RFUs and thresholds with these new instruments, because this single homozygous peak here is at 26,000 RFUs. And so I've blown this up to a scale of 1,000. And so you can see here, I'm getting bleed through of the blue peak here and bleed through of the two red peaks here. And we're talking about bleed through occurring at around 300 or so RFUs. So your analytical threshold, first of all, is going to be much higher. And then you also are going to have to look at a stochastic threshold that's also much higher than what you're used to looking at with a 3130. So this is 30 picograms of DNA. So we're seeing dropout here. This is dropout of a 31.2. The surviving allele here is 600 RFUs, 630. Here's a surviving allele. The 19 is dropped out. It's below our analytical at least. RFUs at 460. So this is going to create, a lot of. It's going to take time to get used to these different thresholds. So I made a change here. The default. This is the default injection, 15 seconds. In your handout, it says 24, but this is the 15-second, 1.2 kilovolt injection. So once again, doing the heat map at 30 picograms, we're starting to see these yellow boxes where we're getting dropout occurring. At 10 picograms, you're getting a lot of locust dropout. So let me just sort of okay. There we go. Just looking at the 30 picograms, we see that the highest surviving peak is 753 RFUs. So you may want to go up to 775 or something like that to be able to use that as your stochastic threshold. So again, the new kits, the new instruments is going to create a reevaluation of your thresholds. This is a paper that John Buckleton's group published, the ESR, on looking at examination of variability and parameters for identifier. And one quote I'd like to pull out of that paper is, the use of bounds applied to data that show a continuous variation is common in forensics and is often a pragmatic decision. So once again, dropout is a continuous, it's as you go down, you're starting to see it happening at different levels. And so it should be borne in mind that applying such bounds has arbitrary elements to it, and there are cases where data will lie outside of these bounds. So you may set your threshold, you may think you're fine, but there's always going to be these exceptions that will occur because you're talking about continuous data and you're setting a quote-unquote hard and fast threshold to it. Okay. Stutter thresholds, I again won't spend a whole lot of time on this, but there are different ways to calculate your stutter threshold. And just taking a look at a review of the literature, Susan Greenspoon and Brad from Virginia Department of Forensic Sciences, division or department? Department now. They were evaluating PB16. They used the mean, the average stutter plus 3 standard deviations. Ben Krenke from Promega uses the mean and 1 standard deviation. For mini-filer, if you look at that paper, Julio Malero's paper, they just used the maximum. So whatever was the highest stutter, that was the maximum percent. So there are different ways to determine your stutter percentage, but most labs may just use a flat 15% because that's what ABI told me to use or whatever. So it may be useful to look at your stutter in your validation, because this trend, as your repeat size increases, your stutter percentage increases. And so if you have a mixture where you have a higher molecular weight allele, like a 21 allele in D18, your stutter percentages are going to be higher than if you have an 11 or 12 allele. So this can affect, or this could create an issue where, that's a stutter peak. It's not a potential minor allele from from the minor component. So how would you develop your stutter filter? Again, there are different ways to do this. This is not, the way particularly, but ideally what you would like to see is 5 observations of each stutter product per locus from a relevant population. So for each locus, you'd want to see 5 stutter events. And of course, for FGA alleles, typically the longer repeats in FGA you're seeing mostly among African Americans and so forth in the U.S. So you want to determine that too, because the wider your allele spread, the greater your stutter percentage you'll see. So typically you would want to use DNA input quantities from about 0.5 to 2 nanograms, but you may also want to look at very low levels, so like 150 picograms, because you will see that the low level can have skewed stutter, and you can also see where excessive DNA, so 5 to 10 nanograms, can skew your percentage. So I once knew a lab that in their validation, they were using the dilution series from 10 nanograms down to 100 picograms, and for stutter percentage, they took the average overall, so they were including stutter from 10 nanograms of DNA, so they were greatly skewing their overall stutter percentage. The general trend with stutter is that, typically with a tetranucleotide, as your repeat length increases, the percentage of stutter will also increase. With penta repeats, like penta D and penta E, this average tends to be much lower, and so your stutter percentage is less than you have with a tetranucleotide repeat. But if you're doing low template DNA, so if you're down in the 100 picogram range, this sort of curve here, this line, gets shifted. So what would be right here an average percent stutter using a normal kit, normal input, if you're using 100 picograms, then you're sort of skewing the percent stutter. So that's sort of a general. This is just sort of a general trend that you would observe and have to be aware of. So again, I'll just show you a couple of other examples here with D3, and John and I were talking about this during the break. So you see that this is a median absolute deviation. It's kind of like a standard deviation for D3 with the, notice the deviation is quite low, less than 1 with 14, 15, 16, and then with 17 and especially 18, your deviation starts to get really high, and that's because you start to see this greater spread of stutter from about 9% up to 11% with the 18 allele, and this is probably a function of the motif here, where you could have different repeats here versus repeats here. So there's not just one standard repeat going on here. You have families, you have different groups of repeats that you can see that especially too with microvariants. Here's Tho. This is a nice one because you can start to see as you get 6, 7, 8, 9 alleles, and then you get 9.3 of Tho. Well, the stutter percentage is the same as the 6 allele, which is basically here. You have 6 repeats, you have the microvariant, then you have the 3. So that microvariant breaks it up so that your stutter percentage is basically equivalent to the 6 allele because of that the breaking up of the repeat. So I talked about this quite a bit in the introductory talk with the SWGDAM guidelines in discussing stutter, and the reasons why it's important for mixture interpretation is because in this case here, this is the ISFG recommendation number 6. If you have a stutter threshold at this point, and this is your, say, stochastic threshold here in red that I put in, and you have a major contributor and you have this other peak, you could be pretty confident that this B allele is stutter from the C peak, and you most likely have a homozygous AA individual. However, if your peak in that B position and if the A peak are both below your stutter threshold and above your stochastic threshold, then it's very possible that AB is a potential combination of your minor contributor. So you have a CD major and a potential AB individual. You could also have an AA homozygote. It's above stochastic, and that B would be stutter. You could also have an AC. You could also have an AD. And in this case, because I drew in the threshold, we wouldn't say dropout. So these are possibilities that you have to consider with stutter when you're having alleles from the minor contributor that are quite low in that range. So stutter can vary across profiles, loci, or alleles. It's very problematic for low quantity DNA samples, and you should make the determination. You should decide at what point do I need to turn off the stutter filter and reanalyze this data in GMapper without the stutter filter on, especially when the minor components are nearly the same height as your stutter peaks. Peak height thresholds, again, this is some of this is a review. So you know that if you take the same sample and you amplify it 3 different times, you will probably get 3 different peak height ratios. It doesn't necessarily have to always be, in the middle here, 98%. So this can be variation you can have between different PCR amplifications, 71%, 79%, 98%. So peak heights will vary from sample to sample, even for the same sample amplified in parallel. With low template DNA and when you're in the stochastic effects, especially if you're looking at these enhanced interrogation sort of techniques with additional cycles and additional polymerase, you can have elevated stutter, although it's not necessarily that you do those increased TAC and increased cycles. If you're at low levels, you can have a situation like this, where you get a very high stutter peak from this 12. This is a single source sample, but it's a very low template. And so the stutter is greatly exaggerated, 64% of the 12 allele. Here is once again, when you're getting below the stochastic threshold, you're getting down below the stochastic range, I should say, you could get unequal sampling. So when you go to pipette, you're not taking out an equal number of alleles, and so you can get this discrepancy of peak heights. So how would you calculate your peak height ratios? Well, from your validation studies that you could use, you already used the data that you generated for your sensitivity series, different amounts of DNA. You could look at non-probative single source samples with good quality profiles with amplified with different amounts of DNA. Or you could look at, perform these for each kit validated as peak height ratios for the same locus amplified with different kits. So this is some suggestions that Charlotte Word gave at the Promega meeting, and again, you can get this presentation off of Starbase. Other methods, you could use casework samples, so using known standards, and you can calculate your peak height ratios based upon the data that you've already generated, so you don't have to do brand new studies. So single source samples with good quality DNA, looking at different amounts of DNA. So you could also use database samples, but again, just make sure that these are the same procedures that you're using for casework. Make sure that you use a sufficient number and variety of samples to get representative data, especially for loci where you have a wide range of alleles like FGA and D18. So this is the program I was telling you about from Dave Dewar. You can see that as the spread increases, so at D18 you have we had 10 samples in our population studies where there was a 28 base pair difference between each allele. So you can see that the peak height ratio is decreasing. So the greater your spread, the more you're seeing a decrease in your peak height ratio. So you can look at the range of the peak height ratio within a locus, look at your minimum versus maximum percent. So you can do a minimum or maximum. You can look at the mean and the median. And overall, alleles that are further apart tend to have lower peak height ratios. So this is just looking at, again, this is looking at over 8,000 alleles. So this is just a compilation of all of the data that we generated from all of the loci, from all of the markers in the kit. So we're looking at over 8,000 alleles. The typical trend is as your allele difference increases, so you have alleles that are only one repeat away from one another versus alleles that are multiple repeats, 10 or so repeats away from one another. The general trend is that your peak height ratio is starting to greatly decrease. This is down into 70% here for 42 base pair difference or so. So as I mentioned in the SWGDAM guidelines, you should base your peak height ratio requirements on empirical data from single source samples. And so this can, of course, vary. This is Todd Beal. I'm going to skip through some of this because Todd is going to show an example of how he developed this and how he uses it. So I'll just give you a quick before and after. So, and Todd will talk more about this later. So if you have a situation like this, where you have a mixture of two people, so this is based upon the entire profile, not just this one particular locus, and you've determined also that you're about a 2-to-1 ratio of individuals here, and you have a 150 stochastic threshold. Is it possible that all of the alleles are present? Well, if you just look at it and say, well, yeah, they're both well above threshold, so I'm fine here. I'll include that in stats. But if you consider the fact that you're down here at under 400 RFUs, and you can have some variation going on in your peak height ratios, using what Todd has developed, is it possible that a portion of this, say, 16 allele or the portion of the 17 allele could belong to one individual, and the other individual is the 16, 17, but it's just the peak height ratio is what you would expect with his. Let me get to this point here. Once again, Todd will go through this a little bit more, but based upon what he has observed, it's possible that one contributor is contributing 126 RFUs of this peak, and therefore it's possible that the surviving peak or the other peak is not present. So would he feel confident that all of the alleles are present in this particular situation? No. So that's one way that you can use your peak height ratios to determine if all alleles are present or not. So this is just determining your peak height ratio. This is, again, all of the data that we generated at NIST. Most of the peaks are at greater than 1,500 RFUs, so you may want to have a different threshold if you have high RFUs versus lower RFUs. Okay. So to summarize, validation studies are necessary for establishing thresholds for mixture interpretation. So in addition to testing only single source samples, mixture should also be part of your validation study too. So a lot of the thresholds that you're developing, your analytical threshold, your stochastic threshold, your stutter percentages, your peak height ratios, a lot of this you're developing from single source samples, but I'm also doing mixtures, so I'm applying a lot of this information from single source to mixture. So it's also a good idea to include mixture combinations, different ratios, different inputs, 1 nanogram total input, half a nanogram total input, so forth, and just sort of get a good feel of this for your as part of your validation study too. Okay, so I'd like to thank a lot of people, my group, a lot of people I work with at NIST, Becky and Erica and Pete and Dave Dewar and John Butler, of course, Catherine Grishak and Robin Cotton, Charlotte Word and Todd Beal and Bruce Hodebreck and Joni Seguela. So thank you so much. If you maybe have time for questions, I finished a little early, but we have some time for questions. Or feel free to jot them down. Yeah, so the question is, the question is about the using Pristine DNA for validation work, and then we're using it for casework. I think that it's important in your validation studies that you really learn your system. And the way you can do that is to use the controlled Pristine samples that you know the concentration, you know the dilutions, you know the genotypes, and so you're getting a good feel for your system. So I think that we need that Pristine data to help us understand the system and then utilize that in our casework samples for interpretation. So I think it's important to have both. But the Pristine data is certainly necessary for developing all of these thresholds.